Okay, I started the recording. Shout out GoPro Slow-Yo for the increase in my quality. Thank you for buying me a snowball. And we're gonna run that last song back one more time because that was a banger. Okay, so the time has come. It's been requested. I said I would get around to it, and I finally got around to it. So today we're going to be showcasing how to create an emulator for Yan85. I know for the later challenges, like 17, 18, 19 is slightly different. If I remember correctly, in those stages, it's not just running predetermined shellcode. You provide your own shellcode. But using this tutorial and creating an emulator in this way, I think you'll start to understand where my mind was at when I eventually got to those challenges, because it only takes a few minor modifications to this emulator to basically just get the emulator for those challenges working. Why didn't I put this in a separate pane? Alright, I'm gonna close this and we're gonna work over here. Okay, so this is generally what the layout of all my reverse engineering folders look like. Like if we take a look at 17, take a look at 18, 19, you see it basically comes down to creating an emulator for each stage. And what's really cool about creating an emulator is that you're basically taking the emulator that they've written for the challenge, right? And you're rewriting it in Python and providing yourself with all the debug information you need to generate the proper input to get the actual challenge emulator to do what you want it to. So let's get into the Alright, so I haven't peeked at my previous emulator examples before streaming like I should have. So expect bugs. Expect this to be just like my first time doing the challenge. So I will approach it as such. I use PwnCat to download the challenges, but I won't show that now because I've already downloaded it, so we're just gonna go with that. Actually, you know what? I will show that because maybe some people have been struggling with figuring out how to get challenges local. So let's go ahead and get Home College running. We're doing reverse engineering 16. I'm only gonna do 16.0, but I will glance at 16.1 to show you guys how easy these reverse engineering challenges become once you create an emulator. I know you've probably looked at the Home College Discord, the reverse engineering challenge. You see everyone saying, oh yeah, just write an emulator, it makes things way easier. And I think after watching this, you'll see what everyone's referring to. And I will say, I highly recommend writing your first version, your first emulator implementation as early as possible. So like the first challenge where they introduce an emulator, just go ahead and start writing your own version of the emulator, because it's going to make doing literally everything after way easier. And you're going to need those skills And I believe in baby mem it shows up again, and it definitely shows up again in the later toddler 1 challenges. And having the ability to write an emulator becomes really useful in testing your exploits and debugging what's actually going on. And also, it lets you generate, you can like get rid of the actual emulation. You can use it as an assembler in a disassembler, even when you're not actually emulating some code. So, but hold on, let me turn myself down because I can hear myself talking. it's messing me up. And let me get the chat open. I see what you asked, Oreo. Give me a second to get the chat open so I can respond more timely to that. And is it a custom GDB setup? Yeah, I got answers for you. Give me a second. All right, I have got the chat open like a good streamer. Yeah, so my GDB, I use Jeff. I think that's how you pronounce it. GF. GDB. You go here. It's GDB enhanced features. Generally, if you're going to be using GDB to debug something, you're either going to be using Jeff, you're going to be using Pwn debug, or I think some people use, I think it's called like PETA GDB, but most people end up using either Jeff or Pwn debug. Now, which one you use is up to preference. When you begin to understand what you need to be looking at in the debugger, how it presents itself in these debuggers becomes fairly trivial. Like, it doesn't matter. But personally, I like the way Jeff presents information. Like, if you look at this screenshot here, you see it color codes really nicely. Let's try to take a look at Pwn debug and see if they have any screenshots of what theirs looks like. Okay, well, and also I can close this on desktop. Have I wrapped Pwn tools in GDB? What do you mean by that? Have I wrapped it in GDB? Pwn tools has GDB support built in. Pwn debug and Pwn tools are two different things. So what you're gonna do is in your GDB init, which should be in your home folder, right? So if I do .gdb init, you're either gonna source this file from wherever you end up downloading Jeff, right here, opt jeff/jeff.py, or you're gonna source opt/pwn debug GDB init. And actually, I can show you GDB real quick, in both forms, because I forgot I set it up like that where I can just comment it out. So I'm not gonna actually do any debugging yet, but let's say we start it. This is what Jeff is gonna look like. I like the color scheme. I like just the way it looks, and the way it presents information to me is really nice. Like, if I want to look at the stack, I can use telescope, RSP. Let's say I want to look at 30 entries on the stack, and going from the top of the stack, it's color coding for me what is actually an address for code, what exactly is a stack address, and then it makes it easier when I'm looking at these. I can see what's data, what's code, and what's a stack address fairly easy. If I go back to GDB init, right, and I comment this out, and I use Pwn debug instead, this is what Pwn debug is going to present information like. Also color coded. I don't know if it has a telescope command. I hope so. Okay, it does. I guess you just provide a count. So this is what Pwn debug looks like. Same idea. It's just too much information. I feel like Pwn debug throws too much information at me. Too many different colors. Like I said, it's up to preference, but I personally like the simplified view of Jeff. So that's what I use. Both of them will help you get the job done. I know some people prefer Pwn debug for like heap analysis stuff, but yeah. Consumer of THC. We're gonna be writing an emulator for this Pwn College challenge, babyrev, to solve it. So I'm gonna basically walk through how I reverse engineered it, and then how I start to put together an emulator to eventually solve that challenge and the following challenges fairly easily. So that's what we're gonna be doing today. You've been asking me to do it for weeks. Finally got some time to do it, so we're gonna crank it out today. Yeah, I knew you were custom. I could tell just from the name. Kowalski saying hi was a giveaway too, but yeah. Okay, so let's go ahead and switch back to Jeff. I think I did show a little bit of what their custom architecture looked like. It's only a 1 byte. I don't know what the terminology is, but I think it's like a custom ISA technically. A 1 byte ISA. Yeah, the registers are all 1 byte, and then the opcodes break down to, not the opcodes, the instructions break down to 3 bytes. 1 for your opcode, 1 for your first argument, and 1 for your second argument. And you'll start to see this when I get into reverse engineering. So let's go ahead and get Ghidra open. Hopefully I don't have any previous, okay. Yeah, hopefully I didn't have anything open to spoil. But we're gonna go ahead and find babyrev16. I did say I would show people how I download stuff using Pwn. I need to actually start it, so I will show you that. It's pretty self-explanatory. You set up your SSH key in Pwn College. I'll leave that as an exercise for you to figure out. If you've made it this far in babyrev, I'm sure you're capable of it. Important to remember, this is where our challenge binary is going to be. Retrieving that is as simple as just download /challenge/babyrev, and it's going to download this to the current directory. I'm not going to run it now because I don't know what it'll mess up, but like with the Ghidra and stuff, but that's how you do that. Okay, so you've made it to babyrev, you've downloaded it, and you're ready to tackle this challenge. You're like, okay, people keep saying 16 is where stuff starts to get hard. We're ready to dig in. Let's get to work. So, you know it's an ELF binary. So, the first thing you're going to want to do is when you open it up, if you don't have symbols, you're probably gonna be looking for entry or start, and then you want to eventually make your way to main. In the stream, I'm just going to talk through my thought process in approaching this challenge. So, you open it up. This is definitely very intimidating the first time around, but you kind of just have to like take a moment, read, see what's actually going on here. And honestly, even without fully understanding what you're doing in these early stages, just getting something that works and like doing it in repetition in level 17, level 18, level 19, and then the challenges further after that, you're going to start to understand this architecture way better. And the cool thing about writing an emulator is I know some people kind of just try to like reverse engineer the code. They extract the code from the VM and then they just try to like figure out what does what. But in creating an emulator, you sort of see what the design choices went into creating their emulator, right? Because you're basically just rewriting what they did, and you, in doing so, you develop this understanding of like, why is this here? And I think you will start to see that once I stop my tangent and actually get to writing the emulator. So let's do that. Let's do a little bit of reverse engineering first to figure out what we're doing. My initial approach was, well, I know it's like a emulator or virtual machine, so I'm just gonna copy all of these interpret instructions. I'm just gonna copy all the functions in here and translate it to Python, right? Because Python's what I'm more familiar with. I'm sure you could just straight up use C and just fix that. I know someone said they did in the Pwn College Discord, but what I did was I just wrote it in Python and I used the C types module, which let me basically use stack addresses to, it let me use stack addresses, it lets me use libc functions, which is used in these executables to do everything that's happening in this C-based program in Python. So to what I was talking about. So what I normally do is I open up main, I take a glance. I might read these in here, but I normally prefer to literally just run the binary and see what it says. And when you do that with this challenge, you get smacked with output. So you can see that some instructions are happening. I'm trying to get to the top without going too far. Here we go. So they tell us this challenge is a custom emulator. It emulates a completely custom architecture that we call Yan85. You'll have to understand the emulator to understand the architecture, and you'll have to understand the architecture to understand the code being emulated. And you will have to understand the code to get that flag right. Okay, so this level is a full Yan85 emulator. You'll have to reason about Yan code and implications of the emulator, of how the emulator interprets it. That's what that says. And then it starts this loop and it starts reading instructions. So, did I finish the course? No, I have not finished the course. I have 2 modules left. I think I'm gonna end up finishing this maybe today or tomorrow, depending on what I have to do. And then I need to do the last module, Toddler 2, and then I will be finished with the course. Highly recommend the course, really good course. I think it's the best resource for getting into low-level binary exploitation and reverse engineering by far on the internet. Props to Yan and Kanak for putting together such an excellent resource. So we see it's executing instructions. I know some people just look at this and then try to figure out what it does. Personally, that's not what I'm not getting jiggy with that. I'm not getting jiggy with that. So it says key, outputs key, and then it expects some input. Then let's say I give it input, what happens? It says incorrect, and then it returns. So my first thoughts when I saw this was, okay, so it's taking some key input similar to like the earlier stages of the reverse engineering module. Will I stream other stuff from the course? So I originally planned on streaming more of Pwn College, but the problem is you can only do like the first 2 levels, which in most of the modules, that's not really enough to get into the meat and grits of what the modules are actually about. But this reverse engineering module is a decompiler. I was thinking about it just to get that experience with figuring out how that works, but it wasn't necessary. So we're just gonna focus on an emulator, assembler, and disassembler for today. The neat thing about writing emulator is you can roll it all into one. So as I was saying, so you see you get a key as input, and then that determines whether or not you get the flag, or at least that's what my assumption was. My assumption was if I provided the right input, it'll give me a flag, right? So how do we figure out what the right input is? You can go about looking at this output here, right? Finding where comparisons happen, because they do happen. They aren't mean enough to make them do some weird obfuscation techniques. They're pretty straightforward. I'm pretty sure they use the compare instruction. I'll try to look through here real quick and see if we can find it. I don't remember how this challenge is set up. I know some of the other challenges it uses straight up bytecode, but I think this one, let's see what happens in interpreter loop. It interprets instruction. Yeah. Okay. So then this is in memory. So let's go ahead and set that up first. I think I've already added more than what was previously there. So what I will do, I will actually download it and start over. I will go ahead and, because I think I've added debug information that isn't there. So let me just go ahead and, how do I delete that? How do I delete this and just start over? Delete, or just look at that. Okay. Probably close the window. Honestly, you said not using oh my god, switch the window. Not using a pirated IDA. It's because I got a new computer and I didn't feel like going through all the trouble of getting IDA again for my desktop. And this isn't a VM, so I'd have to do it for Linux too, so. Okay. So let's go ahead and delete this. So that I see what you guys saw. I know I definitely changed some stuff. I'll actually delete both of these. Let's go ahead, re-import them, reanalyze, and start with a blank slate. Rev 16.0. Okay. Let's see what this looks like now. So I do remember having to change some types and sizes. And you're gonna have to do that for later challenges as well. Okay. So, this is what I wanted to show. So they're nice enough to give us debug information, so you can sort of assume what these are gonna be, but obviously you should check in doing your code review. But here we have VM code, right? That gets copied here into local 418, and then local 418 gets passed into the interpreter loop, right? And then starting at this address, it appears at hex 405. We're storing a byte which determines what instruction we're at. Let's see, because this is going to start with 0. It's initialized to 0. And it adds 1 every iteration. And then we can see at each address, it looks like it's taking 3. Let's go back. At UN3, so it looks like it's taking 3 bytes at a time. That's probably why it's incrementing by 3. Yeah, so you want to do 0, and then you want to go to 3, and then you want to go to 6. So you multiply this by 3, and you're starting at this base address. Okay. So that looks like our instructions, and we can start to put together some more useful debug information. So going from there, I'd probably rename this to base address and start to carry over that information to every function where I see it gets passed as a parameter. Okay. And immediately you notice that the base address gets passed into all of the instructions so that they're aware of where that is. And then it looks like param2 is going to be the instruction. Alright, hold on, I'm getting a call. Okay. Alright, over. It looks like these instructions. Alright, hold on. Give me a sec. Alright, I'm back. Okay, where were we? Okay, I almost thought I forgot to start the recording. Oh my goodness, why is Twitch being so weird? Hold on, I gotta get the chat back open. One second to get that back. And we can get back to this show. Okay. So we can also use the output of this to get a better understanding of what's going on. So it looks like these are registers named A, B, C, D, S, I, F. And that's coming from this output here in the interpret instruction function. So these must be the registers. It looks like our registers start at the base address plus hex 400 all the way until hex 406. Okay, and these are our opcodes. We see. Let's see. They shifted over 8 bytes. 8 bits. No. 8 bits. 8 bits. I said 8 bytes. 8 bits. It shifts it over 8 bits. Ends it with hex FF. So, and then it outputs that. So it looks like this is extracting the opcode argument 1 and argument 2 from param2. So then going back here to main, where we see VM code being copied into the base address, we know that this is an array. And sort of to see what these values are all together, I would go ahead and change this to a char. And this is good because it lets us do this. If we wanted to, when we eventually get around to extracting the VM code, it becomes as simple as going to copy special Python byte string, and it'll copy this entire character array of instructions to Python byte string for us. This is VM memory. It looks like it's a similar setup, but it looks like everything's initialized to 0. I don't know if they already have pre-initialized variables. I know they do for some levels. So for the sake of just being sure, we're going to extract the VM memory and use that as well in our emulator. So let's go ahead and convert this to a character array 2. Okay. Yeah, these are all initialized to 0, but for some of the challenges, it won't be. So keep that in mind. So yeah, so we see there's a while loop that executes all the instructions. It calls interpret instruction to parse the current instruction, figure out what the opcode is so that it knows which instruction it's referring to, and then it calls the instruction. One other thing to note, the way it ends these instructions, I wouldn't be surprised if you could run multiple instructions at once. I don't think you need to do that in any of the challenges, but it's something that would be possible, I believe. So let's get into writing our emulator. Let's start VS Code. Oh, no spoilers. Hopefully I didn't spoil anything for anyone there. I don't think that's a working exploit anyway, so we're good. So I'm just gonna create a new file. Yes. And really tempted to just like copy some stuff over, but let's do this. I create a class, and for the first steps, just literally copy all of this stuff over and rewrite the code that you see here in Python. That's literally all it comes down to. It basically is copy and pasting. It's just glorified copy and pasting. So let's get to work. Trying to think of like the fastest way to copy stuff. Yeah, I think we can just do this. Hello? Why is it doing this? Put it in the corner. Okay, there we go. It would be easier to copy in C, but who wants to deal with that? They don't have to worry about like what all the proper includes are, and I'm not familiar enough with C for all that BS. So, and I'm gonna be using C types, so it's gonna be pretty similar in Python. So, all right. Speaking of that, let's import C types. And then let's create an init function. Let me see, it's underscore main. I think I've been using Python enough to know, but we're just gonna go with that. Alright, now we just copy functions over basically. I'm just gonna copy this. Actually, now that I'm thinking about it, I don't think I ever ended up using these describe functions. I don't think these are necessary, but I will copy them. I won't put code for them yet though. We're gonna go in order of importance. What's gonna actually affect functionality? Go from there. And let me do this. Always on top, so we can just describe. Okay. Now I could literally use shorter names, but just to show how much copy and paste this really is, I'm gonna use the exact names. Ugh. And also, this may seem unnecessary, but this goes back to what I was saying about having like debug information. So like for the 0.1 challenges, like 17.1, 16.1, these functions aren't going to be named for you. You're going to have to figure out what they are. And in doing so, you're gonna be able to figure out. Let me go ahead and show. You're not going to have these pretty little prints that show you of the 3 bytes, which byte is going to be your opcode, which byte is going to be your arg, and which one is going to be your arg2, R1 and R2. So what ends up happening is you crack open these instructions, and you're going to see that hex 10 here, it reads from param2 hex 10. So that must be arg2, because it expects, if we go look at these print, it expects, I'm looking at the wrong one, here we go. It expects arg2 to be the immediate, it expects arg1 to be the register. So if it's calling write register and it's ending param2 with oxff, then that means that arg1 is going to be the first byte, right? And arg2 is going to be the 3rd byte, going from right to left. And then the middle byte would be the opcode. And we saw that in the print that it gave us, but in just looking at this interpret m, we can figure out what the actual structure of the instructions is going to be, and that's going to be useful you can export the entire program to a C file. Honestly, this is the way I did it the first time around, and that I've been using for all the other challenges. So that may be simpler, but that also means I'm gonna run into even more issues than I might run into doing it this way. So I'm just gonna stick with what I'm familiar with now. If I was just like on my own experimenting, then I'd try what you were saying, but this is supposed to be a tutorial for me to show people how I work through it. So I'll just do it this way, because I know this way works, you know. Okay, so let's get back to doing this. Hopefully I'm not boring you all too much, but hey, you want to write an emulator? Here's the way that works. So mind you, at this point in writing my emulator the first time around, I did not know what any of these interprets did. Looking at the names, you can sort of guess. You've used assembly before, you know what x86 assembly looks like, so you can assume what they do. But I hadn't actually cracked them open yet. I just literally cracked open VS Code and started copying. What did Lucas say? Lucas said, fake it till you make it. So I'm just gonna skid my way through this. And a really cool thing in creating an emulator, you can begin to automate the process of solving the challenges. You can do the same thing with the 0.0 challenges, right? Because it outputs the debug information you need to parse to figure out where the comparisons are happening and what the values being compared is. But in the 0.1 challenges, you don't have that. But when you write your own emulator, you always have that output. So then all you do is update the order of your arguments in the instruction, and voila, your emulator works perfectly fine for the 0.1 challenges. You know exactly what instructions are being executed when. All you do is copy the VM code. You find where VM code is, you find where vmmem is, throw it into your program, and you get a disassembly of what instructions are being run, assuming you get the order right. I'm gonna put these interprets next to each other. Just because I know I'm gonna be looking at them very often. Okay. Now we need read memory. We're gonna take a look at read and write memory, and we're gonna take a look at read and write register. Just to figure out how is memory working, how do registers work in Yan85. We're gonna go ahead and take a look at that. Okay. So we have our prototype. Now we need to start setting up C types. I'm trying not to peek at what I use, so types create buffer. So how do we create a buffer in C types? If I remember correctly, you can multiply it by something, and it'll give C types array. You see this CDLO and how it's used to load libc? It means we can load libc into our Python program and call the functions exactly the same way it'd be called in the actual program. So I'm looking for a way to create an array. There we go. Multiply the data type by a positive integer. Okay. So let's create our own address space, right, to work in. The cool thing about C types is it lets us work on stack addresses, which means it's effectively exactly the same as what it is in the C program. So, think we can do base address equals C bytes times, and let's just give ourselves a lot of space to work with. Overkill. But why not? That's an arbitrarily large buffer. Technically, based on what we've seen, we only really need maybe up to hex FFFF, because our registers are at hex 400. Let's go ahead and look in Ghidra and figure out a bit more about what this program is doing. So we see read memory appears to start at hex 300 from our base address. Remember, the base address gets passed into all these functions. For example, we can take a look at the interpret immediate instruction. We see, oh no, that writes a register. There we go. Write to memory. It passes the base address here, and then it reads an offset from a register, and then it gets the value that it's writing from another register. Here we go. So starts at base address, VM memory begins at the base address plus OX 300, and then we provide an offset in a register. Okay, so we can start to see what's really going on here. At 300, remember, we can only, our registers are only 1 byte large. So the largest offset we could store is hex FF, right? So that means VM memory goes from the base address plus 300, right? Because we can provide 0 in a register, all the way until hex 300 in FF. So hex 3FF, right? And then we saw in our read register that the registers begin immediately after VM memory at OX 400, and it goes from OX 400 to OX 406. Now, where does our code go? Where is VM code? Let's figure that out. Actually, we know where that is, because it's mem copying VM code to our base address. So that means our base address is probably, our VM code is probably being stored in these first 300 bytes. What is VM code linked? This is another useful thing they give us. They literally tell us how much VM code there is. And this was also useful when I was writing my emulator the first time around, because it helped me verify that I was copying the right amount of data. Let's change this type to an int. Yeah, I'm not sure what this number actually is, but I'd probably copy this as a byte string too, and then use pack and unpack in Poem Tools, because I'm lazy. Okay. So now we know what the structure of this VM's memory looks like from doing a little bit of reverse engineering. We know starting at our base address all the way up until OX2FF, we have code. And then from OX300 Okay. And then from it's 2b2. It's 2b2 hex 2b2. I'm not sure what that is in decimal though. And then we know from hex 300 to hex 300FF is our VM memory. And then we know from hex 400 to hex 406 we have our registers. Now in creating our own version of this emulator, we can mimic this structure on our stack and do everything relative to this base address. Is it really 690? I mean, that is 16 times 2. Let me see. I think I might have just cast it. Let's just... Yeah, I don't know. Well, when we go to VM code, it tells us that this array... Oh yeah, I guess that is right. 6. Yep. These 2 extra zeros. Yeah, you're right. Okay. Yeah, let's go ahead and update this. Where is the thing to change the data type? Is it not in here? There we go. Oh, it's already set to 690. Didn't include those. That's so weird. Okay, let's get back to actually writing the emulator. So we know what the memory layout looks like. We've used C types to generate a byte array on the stack that's gonna be this big. I'm gonna make this smaller so it doesn't take as long to start up. Okay, so now we can get into actually filling, to actually writing stuff. Let's start with the interpreter loop. What does this do? We can literally put this side by side and start to copy it, and you'll see how it's basically almost a one-to-one translation from C to Python. So I'm gonna even print out the debug information that they print out. I don't think Python has do while loop, so we'll just have to use a while true. They aren't using any condition here, so it's effectively the same. So, okay. So it reads a byte. I'm fairly certain that this should be an unsigned byte. Yeah, because if it gets too large, the number starts to appear negative. And you'd end up with a negative offset from our base address. So we're going to use ubyte. What is that? What is that? There we go. So from address, oh, let's also do this. We also need to save our registers. Should I just do that in a init? Yeah, let's just do that in init. Oh, I forgot that these need to have self before. Let's just use a quick little regex to fix it. Okay. Ugh. I wonder how long this stream's gonna take. This might have to be a 2-part series, actually. I don't think about it. But this is gonna be the most useful to us. Oops, I'm trying to get back here. So we want self.registers. We're gonna want something to track what the current order of things is in the instruction. So for the sake of this one, we can go ahead and take a look at interpret instruction, and it'll tell us. Opcode is going to be 8. Arg 1 is going to be 0. And arg 2 is going to be 16. X10. Okay. Yeah. And then we're gonna need something for these instruction opcodes. We'll actually populate these with values in a little bit, but let's just get the names down. We have add, stack, memory, load memory, where jump sys, add memory. Put in. Did I miss one? Add stack, memory, load memory, compare, jump sys. Must have just copied an extra one, I think. Add stack. Memory, put in, compare, jump sys. Okay. Actually, you know what? We're here. We might as well go ahead and put these in here. Just put this here and just start copying these over. This is less than 0. I think this may just be a matter of Gidra decompiling it. Weird. Oh, I put this in the wrong one. But I will explain how we fix that there. you'll see it's reading a byte from the stack. It forms the shift, and then it checks if it's less than 0. And I can explain why that happens, but we'll do that when we get to it. We also need to remember top. Let's go ahead and save these with the value they actually are. Let me close this sidebar. There we go. Shift it over by upload, then in that, put this so that it's only a byte, and update that. Okay. Yeah. I think I remember having to do this for something else too, but we'll get to that when we get to that. Let's see what this looks like in assembly. Why is it... Jump not signed. Yeah, so it is checking if it's negative. Alright, well, hex 80 would be negative. So I'm pretty sure this is just 80. That's what it's trying to say. So yeah, it uses hex 10, 1. In binary, these are just 1 in each slot for a byte. So like this would be 3, 4, 4. 16 would be, this would be 1, 2, 8, 16. This one would just be and if we look at this pattern here, you can see that it makes sense that this would be right, because this is 8. This is 0, 1, 2, 3. This is 2 raised to the 3rd. And that's how we get this 8. 2 raised to the 3rd, that's how we get 8 here. There's a 0 prefixing this. This is hex 40. I don't remember what this one is, so I'll just do the other ones and come back to that. 1, this is 2 to the 2nd. So then we have 2 left. Four, 0, 1, 2, that's here. That's here. So if we just look, we have a 1 here, a 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. So it's just using a 1 flag in each position of the byte to represent the opcode or the instructions. And it 1, 2, 3, 4, 5, 6, 7, 8. We have 8 instructions, so it works. I will just comment these out as I spent the time writing it out, so we're just gonna leave that there. That was just to explain how these opcodes are working. Okay. What should we do next? Oh, we should look at registers. How do registers work? We already know how they work here. Okay, so I'm gonna convert this to byte, because this is better for us. Here we go. And then when we look at describe register, also can we change this to byte? These are all C terminated strings. And would you look at that? That's where we get the ABC DSIF from. And these are the opcodes for those. 4 goes to A, and that's this one. So let's get these registers saved. So we're gonna allocate a region on the stack. Well, we're gonna use the region on the stack that we've allocated using this for our registers, and we're gonna put them in the exact same position that they're here. I don't remember how to get addresses. I think it's like address of. Yep. Or was it babyrev that I used? I don't remember. Oh, I think I just used from address actually. There we go. Yeah, from address. And then I can just use address of. Yeah. Now, obviously, I could just index this with 405, but I'll use from address. This is 400. Hold on, give me a second to look something up. I probably should have rehearsed this so that it wouldn't drag out as long, but too late to turn back now. Let me look up some C-type stuff real quick. Okay. How does firm address work again? Alright. Alright, I'm assuming this returns in a number. So let's get back to this. So I'll set 0. So it looks like these names correspond. 4, 10, 1, 8, 2, 40, 20. Or 10, 1, 8, 2, 40, 20. Yep. So let's just look at it from this view. Why did it do that? There we go. Okay. I'm just gonna copy this and then update it. 4, 10, 1, 8, 20. I'm not sure how to even get to these question marks. Yeah. But we need one for 0 too, because that's for 9. 0, 4, 10. What? Oh. I think I use like none for question marks. I don't think I gave it an address though. This is really hard not to peek. Oh my god. Okay. I think this just ends up calling crash, so this doesn't have an address. Let's go back to read register. Yeah. These names are only useful for describe register anyway. I don't know if we end up using that, so. But I'll leave this as it is. Let's do that. 3, 4, 5, 6. Okay. So it looks like that's our instruction pointer in interpreter loop. 405 it's marked I, so I think I'd assume it's an instruction pointer. Oh, go back. There we go. I should really just index self-dot registers for this, but too late to turn back now. Because we're just copy and pasting. So, we want it to be as one-to-one as possible. Lifestyles of the young and wicked. No money, got a new addiction. Money, diet, very liquid, never humble, I admit it. Going hard like we from the Hamptons. I'll take you dancing to the mini mansion. I don't miss it. I'll touch the M, Danny Ocean, I got the plan. No respect Okay, then we call interpret instruction with the base address. Hold on, I need to go to the bathroom. I'll be right back. 30 seconds.
I'll be gone, be stuck, gone, I'm done. Bitch, yeah, she said she wanna fuck. Smoking dope and it's fucking up my love. Counting up like the first of the month. I'ma soak up the cloud like a sponge. Got my dick in her mouth, what she want. And my dick in her mouth, what she want. Gone, I'm done. About to boot up on these niggas like chunks. Praise the sun, ask a no. About to fuck your bitch, did she do my chores? She gon' suck my dick and she gon' do it every Sunday. Bitch, I want this Rari, I'm so tired of this Hyundai.
Right back. Oh, wait. Ugh. Okay, we were writing interpret instruction. Whoa, what happened? What did I accidentally delete? I'm just gonna move this into Alright, now what was it saying about arrays?
Running down the street so I don't get fat. Trying not to stress so I won't just crack. But it's hard to relax when you know you're not in control.
Okay, so you have to call it to initialize it. Okay. That should work. I'm wondering if these may be problematic. I think I did something else. Could be fine though, because we're only printing it. It's not like actually being used in the program. Yay! Interpret instruction. Okay, so we're gonna have to end this, I think. Let's put this on a new line. So we need to read from the offset at that address. We need to read 3 bytes. I don't remember what was the. I think we could just use like yeah, let's do that. Let's do uint from address so memory address, which is the base address like they have there, plus that's going to be the previous value that it was times 3. So instruction pointer val. Right. So that's gonna, and then we just need to end this with x f to get 3 bytes. Okay. Okay, and then let's go ahead and copy code. Let's go ahead and copy those over and load that into memory before we even get to writing our instructions. Hello? My brain is like dying. Hello? Copy the byte string, place. That's not how I wanted it. Python byte string. I was clicking. I was doing the wrong one. Bro moment. Alright, this is annoying. Let me do this so it stops going so far away. Now we just need to load these at the appropriate offsets. How do I do this without? I think they're right after, they're one after another. Okay. And then flag description. I think this is for the jump instruction. Jump and compare. You don't really need to understand that yet, so I won't speak about it. That's 690. I'm so irritated that it's not like copying the last two like it should. I won't get stuck on that tangent. Let's just copy them at their memory. Should be M actually. I think I need to typecast this. I don't think that needs to be unsigned either, so it doesn't really matter though. It should be typecast when it's read by the appropriate functions. Before we even do anything though, let's just test this. Where did this come from?
A purpose worth the wait, and with the crash of nightfall comes tiny
Let's see if those are the same.
when fame and fortune fooled me. I felt my polygons decline, the condensation of a diamond mine.
Oh, brother. That's not good. Oh, that's because I didn't actually, bruh. Is this not a number? What is this then? Oh, I think I need to, yes, because I typecasted it like an idiot. I mean, that's because I think some of the functions need to use that. I think this will fix it though. What about now? Okay, good. So it is copying it correctly. That's weird. Okay. We'll just exit if we ever get it wrong. Okay. We have that. I don't think the register values are ever predetermined. So we can leave that alone. And then just to check, let's check if the first address's value is set to 4. Yep, that's a 4. And then 2 should be 10. The hex 10 or 16. Okay, good. So that's working. So we have our VM code being loaded onto the stack. We have our VM memory being loaded onto the stack now. Now we just need to work with it. Wondering if I should just call the stream here because we have our prototype for it. Next stream would literally just be writing the code for functionality. I think that might be what I do. I will write the interpret instruction function. Yeah, I'll write interpret instruction today, so that we'll see that it begins to that it's actually parsing the instructions correctly. Yeah. Yep. Okay, let's do that. Let's write interpret instruction. And then, for all intents and purposes, filling the rest of the functions with content is something that, after seeing just this this video, you would be able to do. I'd like to think. And then I'll do a part 2 where I actually finish it. Yeah, let's just do that, because how long has it been? It's been an hour and 30 minutes. That's pretty long. I normally do 8-hour streams, but I have other stuff to do today, so let's just do that. Oh, this is the wrong one. Okay. So we're gonna also want to deconstruct it. I'm gonna write a function that does that. This expects self, then it expects base address, which is C times T, then it expects parameter. I think this may need to be dot value. I guess it doesn't matter. We can just handle parsing that in. Yeah, it doesn't matter. We can just pass that like this. Then this would be instruction, and it expects a uint. Okay. Struct. I mean, I don't think I need a deconstruct function. I can just do this. Opcode. And that would be. First of all, let's update instruction with what it should be. Alright. And now we can work with it. So this would be instruction shifted over by instruction struct code ended with FF. So that would be shifted over by 8 and then ended with OXFF, which is what we want. Now we do R1 and R2. This is useful because these will be randomized. And you'll see that it'll be different in 16.1 in the next episode. But this little trick here in storing it in a struct means you just find 3 values here and boom. And then the rest is really just copy and pasting and running it, and then you get a solution. Man, I seriously underestimated how long this was going to take. I think writing my emulator on my own the first time took like 8 hours. But considering the amount of time it would take you to solve these challenges otherwise, that 8 hours makes solving the other challenges take like 5 to 10 minutes. Ugh. Why is this sidebar open again? So instructions. Now we just need to do this for all of them. M, oh, that should be M. M, add, stack, memory, ellipsis.
Yeah.
And then we can just print these out. Now this isn't gonna like actually work yet because we haven't written the emulator. But we can see that it will go through the instructions and print them out. But jumping, you can jump and it's not gonna like honor those jumps. It's just gonna go through and print it in order of how it sees it, because we're not actually emulating it yet. But now we can call the interpreter loop. Probably shouldn't have typecast. I mean, but yeah. I remember why. Okay. Well. Alright, it's looping infinitely. If let's just throw that in there just so it doesn't loop infinitely. Okay, let's get this side by side with the actual program so we can do some comparing. I'd expect the ending to be wrong because like I said, it's not honoring any of these jump and compare instructions. But let's see if it's at least right in the beginning. And 8. Okay, let me output this as hex. Oh my goodness, this is annoying. I can regex though. This is what I need to match. One X code X R1, and we want the hex of R2. Oh, I forgot to get rid of the backslashes. Get rid of this. Yep, that looks right. Okay, let's run it again. Go to the beginning. There we go. So now we're at the beginning. And we'll see that the very first few instructions before it eventually gets to like a jump or something that actually... What did I just press? Oh, I think I went to the previous. There we go. We'll see that the first few instructions are what we'd expect them to be. We see 10, 4, 82, 10, 4, 82, 10, 4, 82, 10, 8, 54, 8, 4, 8, 8, 4, 8. And you can see that it's interpreting these in, it's disassembling the VM code correctly at the moment. So we've basically thrown together a very basic disassembler. You can start to add your own debug information even in this interpret instruction implementation that we have here. So there's that. Now, if we wanted to actually start to emulate behavior, it becomes a matter of, instead of just printing here, we would be performing our own function calls. So this would be like self.interpret m, and then we'd pass param, then this would actually perform actions on memory based on the register and stuff like that, which, like I said, I'll do next stream. That'll probably take an hour to get working. But yeah, so I think this was a good start to get you all headed in the right direction as it pertains to writing an emulator. Let me know if you guys want me to actually upload the source code for this to GitHub. Actually, you know what? After I do the next stream, I'll upload the source code to GitHub and make sure that that it's a more complete, with more like comments and debug information version of that. But let's find somebody to raid.
Perceives all things conjoined, the past, the future, and the present. Everything flows, and all is connected. This eye is not merely seeing reality, it is touching the truth.
Let's check the tap list. There's no way, no one's online. I think the hack list is just broken. Alright, let's see if I know anyone. Oh, we can read Al. Perfect. I can get a break. Let me go ahead and end the stream here. And I'll show how we use libc and stuff like that next stream as well. Okay, I think this is good enough for the recording. Let me stop that.